Hi, good morning everyone and our remote viewers. We'll be discussing today's sensitivity analysis. I think we already touched it several times. First, in the general introduction we had at the first day, we said it's part of our general routine of generating a model. And we'll see today what we mean by that. And we also touched it yesterday when Matt showed us RSM, the Reaction Mechanism Simulator, RMS. So we also saw some sensitivity analysis calculations. Hopefully we'll see today a little bit what it is, what's the definition, how to treat it, and generally what we get out of it. We'll start first with a story. A story of my own boss. So in the community for a while, they knew how to deal with just alkyl chains of carbon and hydrogens, and they wanted to start simulating alcohols. So a group at Stanford, the Hansen group, came up with a way to use a shock tube and measure observables such as OH radicals at relatively high temperatures. You can see here they use nearly 1500 Kelvin and almost 2 atmospheres. And Professor Green said to Professor Hansen, wait a second, just before you run your experiments and see what you get, let us run a simulation. Let's see what RMG can tell us and predict about what we're going to see. They already had some butanol, so we're talking about butanol here, and they already had a butanol model in our group, which was developed for different conditions. First, they ran it just to see what they get. And these are the initial predictions. You can see here OH radical, there's an inflation and some water. That's what RMG predicted at first. Then they ran sensitivity analysis, what we're going to discuss today. And they chose the 5 most sensitive, or the 5 reactions the system was most sensitive to, and they calculated these reactions at a certain level of theory, which I'm unaware what they use in that particular case. So they recalculated it and got a better model. Since the model was sensitive to these reactions, or I should say the observables, the specific observables they cared about were sensitive to these reactions, they got a different prediction. Then the experimental results came along and...
Yeah, can I even add a gloss to this? The dotted line, we had already done this sensitivity thing at a different condition. And we had already refined that model. So the dotted model was really very good at a different condition, at a lower temperature. And then when we redid the sensitivity analysis at the higher temperature, different reactions showed up as being sensitive. And so we had to do different ones.
This verifies that the story is true. So I can repeat that for the remote listeners if they haven't heard. The initial model was already optimized, was already well calculated at different conditions. For 1500 Kelvin, they found different sensitive reactions. They calculated them and got different predictions. Then the experimental results came along, as you can see the red dots. It's not a perfect fit, and we shouldn't expect a perfect fit. The line should not pass exactly within the dots, because that would be a fitted model, which is a model that you change the parameters, you force it to be exactly the same. Great. It doesn't teach us anything. It doesn't give us predictions or the ability to make predictions for unknown territory, for conditions we don't have experimental data for. So if we know we tweaked our physical kinetic parameters to values which aren't really true, we will have larger deviations at conditions we haven't explored, we haven't fitted the model for. So these are considered very good results because they show qualitatively and very closely quantitatively what the actual data also shows. That was an introduction or motivation for why sensitivity analysis is important. If we do run sensitivity analysis, it should answer the following questions. First, how will a simulated observable change with respect to a change in the data? And what is the data? It could be a rate, or several rates, thermal data, transport data, initial conditions or operating conditions, anything you can think of where you have uncertainties, and that's the key. If you're uncertain of the actual temperature in the reactor, well, you can measure it at one place, but it might be different at a different place. You can maybe simulate the entire model at several different temperatures. If you modify the data, you can see how the model responds, and you can infer how sensitive you are to a change, to a perturbation in that data, which can really be anything. Usually, commonly, we'll refer to rate and thermal data, because that's what we care about mainly for our applications, but it can be applied for anything else. We also answer two other very similar questions: which parameters control the observable? We would like to know that. And which parameters shall we further study in detail? As you saw in the previous slide. Everything here again is related to uncertainty. Since we have uncertainty in our data to begin with, as I just discussed an example for temperature, but of course we all know we have uncertainty in rates and in thermal data. We would like to maybe study them further, whether it's experimentally or computationally, but we have so many parameters in a large model, sometimes hundreds of thousands, sometimes in large models, that we would like to know them, but not all of them are that important to make a prediction. And sensitivity analysis is the tool that differentiates between the parameters that affect the observable and that we'd like to study further, and others where an estimate could be just okay, and we can live with it and we'll get a good prediction anyway. Yes?
Just a quick question about the previous graph.
Previous graph?
Yeah.
Yeah.
Is there there might not be an exact answer, but is there a rule of thumb to look at these graphs and say, the 30% different from an experiment are the free energies out by a certain amount, either the PSP or the...
Yeah, it's a good question. I'll first repeat the question. Is there a rule of thumb to know whether the simulation is good enough? Is that correct?
Yeah. Well, just what's the order of magnitude off on the free energies that you expect from these?
I'm afraid, as you also said, there is no particular concise answer. The answer is it depends. It depends on your applications. If you're simulating a process of manufacturing a drug, you have to know it for pretty high certainty, and you might not accept something like that. But if you'd like to know quantitatively when the system ignites, so this tells you, so the graph tells you these two peaks, they're almost at the same time, and it doesn't ignite at 30 microseconds, but about 2 to 4 microseconds. So depending on what you'd like to know out of it. Yes, please.
Yeah, I think in this case, if you look at the left-hand graph, you can see that both simulations and the experiment all agree at long time. And I think what that is really going to the equilibrium value of nBuOH. It probably should be going to the equilibrium value on the right side. So then you say, well, why not, right? I think it's a really great question. I think that it's hard to know. The experimental absolute concentrations in the SHOP 2 experiments probably have errors on the order of 30%, so they might be off. That error, if I drew the error bar on the red thing, it would probably overlap the blue one, but it doesn't mean the blue one's true. And certainly our ability to do the thermo, we're not probably good at 30%, but we're probably not that far off for water, right? So yeah, I think this is really not so clear, actually. But the fact that the other simulation, the dotted one, doesn't seem to be going to the same asymptote, suggests that probably we changed the thermo of some species when we did the refinements, I don't remember, and that must have had a knock-on effect to change the water, but it's a little strange, actually. So it might be worth a re-examination. But again, the difference there is like between 2 and 3, in the 10 to the minus 3 mole fraction. So that's like a 50% difference. That's a less than half a kcal probably, or I don't know if it would.
Thanks. And please feel free to stop me if you have any other questions here or remotely. All right. I'll just emphasize one additional point. In an uncertainty analysis, we change a parameter. The parameter is usually physical, like a rate coefficient, thermodata. It's not my choice to change it or to determine its value. Of course, it's physical, it has only one true value. Because we have uncertainty, we're allowed to change it to see, well, we're also always allowed to change it in a simulation just to see how it affects our observable. Because we don't know the true physical value, we would like to examine whether it's worth studying that parameter in depth. Before we continue, just a general misconception of how we refer to or how we speak about sensitivity analysis. In many papers, you'll see sentences like that: the rate of reaction, whatever, something, R19, is highly sensitive. People do speak like that, and you'll find me speaking like that. It's tempting, it's easy. But it's a trap because our reaction isn't sensitive. The observable might be sensitive to a change in the rate. So let's try to just be aware of that, especially in formal writing. I guess when we speak, it's okay, but also try to speak correctly. Again, a reaction isn't sensitive. A reaction has a physical rate which isn't given to change. It just depends on temperature, sometimes on pressure. But the concentration, for example, of OH radicals at a particular time in our system might be very sensitive, relatively sensitive, non-sensitive to the rate of reaction R19. So let's continue with a formal definition. The normalized sensitivity coefficient for kinetic and thermal when we run sensitivity analysis is defined as the following. I'd like to start from the right-hand side, from reverse. Let's look for kinetics, for example. When we think of a sensitivity analysis, what we are doing, we're perturbing a parameter. So we have delta, we have a change, and we're observing a change in our observable, and that's what we see here. The partial derivative of the concentration of some observable divided by the partial derivative of the rate K of reaction I, and we'll do that for all reactions and see which one is most important. So dC over dK. We're normalizing it. We would like to have a normalized sensitivity coefficient, so we multiply by the actual rate at these conditions, temperature, and of course, of that particular reaction, and we divide by the concentration. Why do we do that? Why is it important to normalize? Any ideas? Why do we need to look at the normalized sensitivity coefficient? Why isn't just dC over dK enough to say whether we're sensitive for certain, whether the observable is sensitive to a certain reaction or not? Any ideas?
If the orders of magnitude are different between species, right?
Right. The orders of magnitude between species are different, correct, and rate. Let's give an example. That's absolutely correct. dC over dK. So let's say I just perturb K by a fixed amount, whatever that is. And I'm observing the change in concentration of two species. The concentration of species A in arbitrary units, just to make it easy, is 10 something in arbitrary units, I don't care. And the concentration of species B is 100. When I perturb Ki, I change the delta in the concentration, let's say was 5 in the same arbitrary units. So for species A, we have a concentration of 10 something, and I just changed it and added 5, so it's a 50% change. For species B, the concentration was 100, I added 5%, so species B is less sensitive. It changed by just much less, relatively, to species A. So species A would be more sensitive to a change in that rate. And we normalize for the rates as well. We have slow rates, we have high rates. And you can say the same arguments for rates as well. I won't repeat it, you can convince yourself. If we reorganize that, we'll have Ki over dKi and dC over C with multiplication, and that's the definition of d ln. So d ln C is dC over C, right? So that's the normalized sensitivity coefficient for kinetics. We'll do the same thing for thermal, and that's important as well. dC over, let's say, delta G, we care about Gibbs energy. So dC over delta G of species I. We will perturb delta G of all species, and in turn, we'll see the effect of each one of them on the observable we care about. Here we normalize for the concentration of the species of our observable. We don't normalize, though, for delta G. Why not? Any ideas? Why didn't I multiply by delta G like I did for K? It's what? Well, it's correct. This form is non-dimensional. This form, well, it has to have some dimensions. We'll refer to that. But why? I don't know. Help me out. Think of an extreme case. Delta G of your species is 0 at the conditions you care about, at a certain temperature. Then what? If you multiply by delta G, you'll get 0 sensitivity for any. So all the sensitivities when you change delta G of all other species will always be 0. You won't have a species you're sensitive. You won't have any differences in the sensitivity. The difference is between delta G and K. The inherent difference is that K is an absolute value. If it's 0, then it's a 0 rate. If it's high, then it's high. K is an absolute value. Energies aren't absolute. It's d delta G. It's always related to a reference state. And you can just change it by changing your reference state. Does that mean you change your sensitivities in the system? No, it's just a reference, right? So you're changing the values of delta G by changing your reference system. So we're not normalizing it for the second case. And here we have d ln C over d delta G without ln. It's not normalized, and as correctly said, the first is dimensionless. The second has dimensions, typically something like mole per kilojoule. And I'll give 3 test cases today that we'll go through and try to figure out what can we refer and understand from the sensitivity analysis. Before that, I'll just show 2 different types of presenting the data once you run a sensitivity analysis. You have a choice. Here I'm showing sensitivity analysis for 2 different systems, so I'm not comparing the system. And don't look at the details. Here I just care about the format, how I present the data. You have a choice. You can present it versus a constant parameter, here time. I'm showing sensitivity analysis of thermal, so how an observable d ln concentration of NH2 over d delta G with units, how that sensitivity coefficient partially normalized, or normalized but not dimensionless, how it changes versus time. Or, very typically, and you'll see that in many papers, you can just present a horizontal bar graph. The difference is, none of them is better, whatever you choose to present. The difference is, once you plot a horizontal bar graph, you should say at what time or exactly the conditions, because you'll get a different horizontal bar graph for different times in the system, right? If you look at 0 here, and you just take the difference from 0 to each one of the sensitivities, at different times you'll get different sensitivities, so it matters a lot at what time. If you want to give your reader and your reviewer the entire picture, that's the way to go. You show the sensitivities when the system advances, if it's time, distance, or whatever. you might want to present horizontal bar graph or vertical, whatever might want to present at one point in time or distance or whatever your parameter is, if you would like to emphasize the data at that point, if it's very important and you have some terrific conclusions to make out of that. My recommendation is to go the first way. Again, it gives a broader picture, but the choice is given to you. So we'll start with the first. Are there any questions about terminology or anything we discussed? Would you like me to repeat anything before we give some test cases and examples? Great. Either everything's understood or either everything's completely a mess. I hope it's the first. All right, so 3 test cases. The first is ethylamine pyrolysis. We have a nice flux diagram here showing you start with ethylamine. The flux diagram is corrected at a certain point in time, right? And several things happen. Let's try to follow it because we'll need it for examples. We don't care about all the details. I can supplement what you see here and say that everything here at the top is important at early times. Everything at the bottom is important at later times, and let's see why. So ethylamine, CCN with all the H's that need to be there. First, when you heat it up, the CC bond or the CN bond, they break. They're the first to react, not NH or CH bonds, which is typical for fuels. So you can break the CC bond, you release methyl radical CH3 and you're left with CH2 and H2, or you can break the CN bond, so you release NH2 and you're left with ethyl radical. So that's important at early times. You don't have other radicals in the system, and that's the only way to go. At later times, you already produced H's and other radicals, and then they can react with ethylamine and decompose it, and undergoing H obstruction, and these are the reactions we get. After beta fission, you release more hydrogen here, which you can see it's an auto acceleration. You release H goes back to react here, and you just consume all your ethylamine. And that's the major route of producing NH2 at later times. NH2 will be our observable that we'll calculate sensitivity analysis for, so we care about that. At early times, that's the major route of producing NH2. So I hope you all memorized that because we'll need that for our example, right? I hope you memorized it. Don't worry, it will be right here on the slide. And here are sensitivity analysis. Here is a sensitivity analysis for ethylamine. We see both kinetics and thermal, and I would like to analyze it together with you and understand what it all means. So here at the top, let's start with kinetics. We have d ln NH2 over d ln Ki dimensionless, right? Again, the meaning is, if you were to perturb all rate parameters in your system by the same amount, what will the effect be on NH2? And let's take the top. Here I chose 1, 2, 3, 4, 5. So the top 5 reactions that's observable is sensitive to. The numbers here correspond to the number on the graph, so that's why we have 7. So what do we have? We said at early times we mainly have dissociations, right? CC bond cleavage, we have it here, and CN bond cleavage. So we have NH2 mainly from that reaction number 2, which we can see here, the red line. So at time 0, that's the only thing that matters. The only thing that matters. Everything else is 0. And these are the top reactions we found the system was sensitive to. Everything else is 0. That's the only reaction that matters. The only source, the only way to make NH2. We don't have radicals in the system. That's what we see here. At later times, it's not the fastest way. The fastest way to produce NH2 is actually via these routes, H obstruction and then some beta fission. So at later times, others kick in, and we can look at number 5, for example. Reaction number 5, let's look for it. Here it is, reaction number 5. I hope it's not too small. So we're sensitive to the rate of that reaction leading eventually to beta scission and forming NH2. Why reaction 5 and not reaction 13, which actually makes NH2? We have a sequence of 2 reactions. We care about NH2. We ran a sensitivity analysis for NH2. We got a reaction here, reaction number 5, reaction number 5 that doesn't even involve NH2. Why are we sensitive to the rate of reaction number 5 way more than the sensitivity to reaction 13, which isn't here? I don't know, help me out. Yes?
This reaction 13 is fast compared to reaction 5.
Correct, absolutely correct. Reaction 13, anyway, is much faster than reaction number 5. That's our model, that's what the model predicts, and that very well might be the physical reality. So the bottleneck of that pathway producing NH2, which is the fastest NH2 producing pathway in the system at later times, which is something I supplement, you can refer, we can understand from here. So that's the bottleneck. So of course you're sensitive to the bottleneck. Elaborate, expand it, you'll get higher flux through that entire pathway. Other reactions, we can look at reaction 7, 4, 1. We don't have to go through everything. I would like to look at reaction 1, as you can also see here. Reaction number 1, first NH2 is, the sensitivity coefficient of NH2 to reaction number 1 is positive above 0, and then it's negative. Interesting. What does it mean? What does it mean a positive sensitivity coefficient and a negative sensitivity coefficient? What does it mean? A positive sensitivity coefficient means, by the definition, I perturb the reaction, let's say I increase it, the delta is positive, I increase the reaction by something, and I get an increase in concentration of my observable. So if I'm positively sensitive to reaction number 2, that means if I were to increase the rate of reaction number 2, I would have gotten more NH2 in the system. Of course, I can't do it physically. I can do whatever I want in the model. Reaction number 1, the sensitivity coefficients of it say, at first, so if I increase the rate of reaction number 1, at first I would observe more NH2 in the system than a base reference, and later I will observe less. That's what it means. That's all you should know. How does that apply to our example? Let's see, I don't know. Let's try to follow it together. Here's reaction number 1. So that's the CC scission. Again, a reaction that doesn't involve NH2. That's okay. So at first, let's try to explain that. Why increasing the rate of reaction number 1 will lead to a higher concentration in our observable NH2? What does reaction number 1 do at early times? Where does it lead? Formation of what? What's important there? It's colored in red. Reaction number 1 goes to, so reaction number 1, are you with me? Goes to hydrogen. It's the main source of hydrogen production at early times in the system. We don't have radicals at time 0 in the system. That's how we produce a very important one that continues to react, and it initiates all these pathways, which eventually, see the H radical here, which eventually lead to the formation of NH2, and that's a very important group. Here. So if I have a faster rate here, I have more H's in the system, wonderful, I'll get more NH2. Beautiful, explained. But we have a negative sensitivity coefficient for reaction number 1 at later times. Why producing more H's is bad for us? We get less NH2 at later times. So it takes a while. So the previous question, I did expect to hear some answers. For that question, it does take a while. You need to know the system, and you just met the system 3 minutes ago. here you need to see some profiles and see the concentration of species versus time, and then you really realize that at that prolonged time, 80 microseconds or 100 microseconds, you barely have ethylamine left, only some traces. It's nearly gone. So if you increase the rate of that reaction, yeah, you'll get more H's in the system, but you don't care about it. You have lots of radicals in the system anyway at these later times. If you increase that rate, it comes on the account of that rate. You'll get less flux going to NH2 here or here, all right? So you don't have much ethylamine left. Yeah, you have plenty of radicals. You don't care about the formation of more H's. You don't have much left. If you want to have more NH2, you would like to direct ethylamine to go to either of the NH2 formation pathways, which is that one at later time. Of course, we're not discussing ethylamine here. It's just an example of what we can understand from sensitivity analysis. You can see the dynamics of the system. I think it's fascinating. Don't forget to supplement the kinetic sensitivities with thermal sensitivities. Sometimes they're even more important. Why? Before we address it, why is it more important? Kinetic sensitivity analysis, let's say I'm showing here top 5 rates we're sensitive to. Maybe I'll end up calculating these 5 rates at a higher level of theory. Perfect, I improved my system. But if I calculate even one of these species, and now I'm meaning calculating thermal, so here I can calculate or measure rates. Here, that diagram tells me I should know the thermal of all these species quite well because my observable that I care about is sensitive to them. So if I calculate even one of them, it affects many reactions. All the reactions it participates in. So you can affect many rates by just calculating one thermal value. And in fact, in that study, we showed we know pretty well the thermal of all these radicals at a nice level of theory. We didn't have a good value for ethylamine, and we slightly improved the literature knowledge of its thermal. Let's look at what that graph tells us. At early times, the concentration of NH2 is very sensitive to the delta G of ethylamine. That means if you increase delta G, first, if you increase delta G of the species, is it more stable or less stable? Species like to be, they're lazy, right? They like to be at a low energy state. I mean, right, otherwise they would have done something and react and turn into more stable species. So if you increase delta G, that's a positive coefficient, sensitivity coefficient, meaning if you increase delta G, so if ethylamine is less stable, you get more NH2. Does that make sense? If ethylamine is less stable, it will decompose faster, creating more NH2. Perfect sense. If it's more stable, the reverse, it won't react. You won't see much NH2. So, all right, so first, makes sense. That's positive. For the others, you can see for these two. So we have couples, right? We can say these two go together, these two go together. These two, if these two radicals at early times, if they're more stable, if you increase delta G, you always increase delta G and you observe something. You observe either a positive change or a negative change. So again, if you increase delta G of these two radicals and you make them more stable, the observable, the concentration of NH2 will be less. So if these species are more stable, we'll observe less NH2. I know it's a bit complicated and just a little bit, but it's not a system you work on. So it takes a while to to visualize it. But principally, these species aren't reactants, they're products, and specific products. Ethyl radical and NH2, these ones, right? They're the products of the reaction forming NH2 at early times. If the products are more stable, the reaction is slower. The products are very stable, so I'm unlikely to produce them. So that's why the sensitivity coefficient here is low. In absolute terms, it's significant at early times, as we said, that's a significant pathway at early times, less so at later times. And we have an interesting phenomena occurring here. I won't go into details. I will just say it's very similar to what we said about reaction number 1. It's positive then negative, so it's negative then positive. These are the products of reaction number 1. That's why it's changed sign. So I hope that example showed why sensitivity analysis is important. We can see the dynamics of the system. We can improve rates. We can improve thermal. Questions about this example? Yes, please.
For the sensitivity analysis, typically, do you have both the kinetics and the thermal being accompanied by themselves, or does one dominate? Like in this reaction, you have like the thermal of the ethyl radical being produced as well as the amine. So if you had like an increase in the rate of the reaction and you had like a more stable product, would the kinetics then dominate the entire sensitivity analysis?
I didn't follow all the way through. Let's see what I understood from the question. You're asking, let's try to repeat it together. If I were to increase the stability of ethyl radical, then what?
Yeah, would you then ignore the rate of the reaction?
Ignore? Sorry.
Yeah, like
ignore the.
Yeah, because you're increasing like the production of the ethyl radical, right? So does the thermodynamic...
If it's more stable, I'm not increasing its production. If it's more stable, I will get less of it.
Oh, okay. So my point basically is, which effect is more dominant? The kinetic effect or the thermodynamic effect?
All right. Thanks for asking it that way. I think it's more clear now. Which effect is more important?
Yeah.
Kinetic effect or thermal effect?
Yeah.
All right. I don't know. I think it's a long question, but the answer is very short, and I might say it's very system dependent. I don't know. It depends on each system, and I think we have a better answer here.
There's several things to keep in mind. First of all, the definitions of these sensitivities are holding everything else constant. What's everything else? We're using the variables K forward, really the A factor for the forward reaction, and also using the delta G heat of formation of or the free energy formation of the species. So in the bottom graph, when we vary the free energy of formation of ethyl radical, we're not affecting any of the K forwards. All the forward reaction rate coefficients are held constant. However, we are affecting the K reverse of all of the reactions that involve ethyl radical as a product. So immediately, something to worry about is that what the sensitivities you get will depend on which direction you wrote down the reactions. Because the forward reactions are being held fixed, rate coefficients, the reverse reactions are varying. So if you flip them around, it would make no difference to the simulation. You flip them around and you use K reverse instead of K forward, you get exactly the same simulation, but the sensitivity will be different because you defined the way we define what our variables are. This is all about partial derivative stuff. Also, what's important really depends on how big your errors are. So for K's, you might have errors of ln K of maybe 2 units. That might be like a factor of 9 if you don't know a rate coefficient very well. If you know it pretty well, maybe it's 1 unit. So that would be, here you might have errors of like 1 or 2 units in the logarithm of the amount of NH2 radical, which would be maybe up to an order of magnitude in NH2 radical due to problems with the K's, possibly. That's what this would say. If the problem is with K reaction number 2, right? That's the one you're sensitive to. The ones that are less sensitive, you'll have less of an effect. On the bottom, say we change the ethylamine free energy, the how big an error do you think we have in the thermo of ethylamine? Might be kcal, 2 kcal, possibly. So maybe be 5 kilojoules, something like that. So this is per kilojoule. So you might have 5 times 0.4 or so. So that might be about 2 Lin units in NH2 also. So in this case, reaction 2 and the thermo of EA have kind of comparable effects, probably, on how certain your number is for the concentration NH2. For every observable, it can be different, and also depends on the uncertainties, all these different things. So it's a kind of complicated question. So Alon's answer was correct.
Yeah, I don't know. And
But you
it's
could
always the
figure it
best
out.
question, the best answer. We have a question for the remote viewers. Did you hear that? Shall we just summarize it briefly, or we're checking?
No, I'm probably not.
Sorry, they not replying. They're not. You're not. All right.
He's ignoring me.
All right. Great.
Oh.
All right. I'll repeat it very, very shortly. The first part of it. Rates are written in a certain direction. So when we change the thermal data, we got it. It's recorded. Excellent. Thank you. So we can continue on. A question? Yes, please.
So when you look at like a flux diagram, if your reaction is mostly carried out by radicals, when you do sensitivity analysis of delta G, don't you expect those radicals to be the confidence we need to know the delta G's most accurately? Because it's propagated. So, for example, here, let's say here the H radical, obviously we can know it well. Let's say hypothetically, as here another big molecule, we have a radical. It is that radical is the one responsible making more radicals. So technically, you expect delta G of that species to be responsible to be more sensitive when you do sensitivity analysis.
Could be. But I think that you actually, these are the 5 most sensitive ones, right? So when you do numerically, these turn out to be the 5. Some of them are kind of obvious, like the ethylamine. You start with pure ethylamine, it can't do anything until it breaks.
Yeah.
Probably, my guess, is that in RMG, maybe reaction 2 is actually written the other way around. Is that true? We don't know.
It's been a while. I don't
I
know.
don't know. It could be written the other way around. In which case, the ethylamine would directly impact the rate of reaction 2.
Yeah, it is, because it's our combination in
Yeah.
RMG. You're right.
So this has to do with the order of the reaction thing again. Okay. The other ones, the H atom doesn't show up, but H atom has a ton of effects, because you want H atom to be stable if you want to make it, but you want to be unstable for it to react. And in all these sequences, you have to make it, and then it has to react. So probably whatever you do to make it more stable will form more of it, but then it'll react more slowly. And so it could be quite complex to figure out what it would do. And again, it might have to do with the order, which direction you wrote the reactions in, what the exact effect is as written here. So not so trivial to figure out exactly what this means, which is why it's good to just compute it numerically and see what it is. Because I'd say my expectations about ROP, of what reactions are going to happen, are much more reliable than my expectations about the sensitivity. So often I learn new things by doing sensitivity. So I would suggest you do it, because I don't think your intuition about what's going to be might not be perfect. It's my guess. I've been doing this for 20 years, and I'm still not perfect.
So my original answer was correct.
Yes.
Nope. Yes, please.
So I have a question about model chemistry. When I was learning quantum chemistry and I wanted to compute properties or reactions or a mechanism, we had to do it all at the same level of theory, because that's the model chemistry that you're using. And the reason for doing that is you can't approach the exact solution to Schrodinger's equation, so you're relying on cancellation of errors to get the thermo correct. Now the approach here is slightly different, right? So you do sensitivity analysis, you find the species that are most sensitive to your observables, and then you recompute that thermo with a higher level of theory.
Which is different than other species.
Which is different to other species, and my PhD advisor will probably start
Scream at me.
shaking points and saying, why are you doing that? Because you're going to start messing up the values of all the other species in your network.
Yeah, right.
Because of the cancellation
Yeah.
of errors.
Excellent question. Excellent question. Briefly, I'll repeat it. When you calculate the Schrodinger equation, since we don't have an exact solution, we would like everything to be at the same level of theory for error cancellation. Here, we'll calculate it at a higher level of theory, so not everything is at the same level, and I'll get screamed at. That's okay. So what we say here, in a model which is gigantic to begin with, right? Hundreds of species, thousands of species. We can't really calculate everything, period, and we can't calculate everything at a high level that we would like to. And so we have many assumptions and many estimations there anyway. So the uncertainties are hard to begin with. And that's one part of the answer. A second part of the answer, we're not solving a Schrodinger's equation. We're not.
That's just by rephrasing the question.
Yeah.
So, if you're only computing the most sensitive thermal data with a higher level of theory,
Yeah.
I mean, the argument against not then recomputing every species is that you're going to cause errors and everything else that weren't there beforehand. And it seems like that that could potentially mess up, the model. But I guess you're saying that it typically doesn't. It typically improves the model when only focusing on certain species with a higher level of theory. So how can you not be certain that the removal of the cancellation of errors kind of idea doesn't make the model it improves it?
So here it's the answer is again, I don't know. It's a different I don't know. Previously it was I don't know and you can't really know. But here I think I might need some help answering that. I'll try my best. I think that we don't have the same cancellation of errors when modeling a system as we do solving a master equation and so on. So just solving a system of partial differential equations. Again, so I don't think we have the same type of error cancellation. And so my experience says, not my intellect, my experience says it does improve the system, as you said. I don't have a direct answer. Bill, do you have a better answer for that?
Yeah, so when you build an RMG model, usually most of the thermo numbers are estimates from group additivity or other not so reliable ways. And so usually those error bars are pretty gigantic, and compared to the error bars in any of the quantum methods, they're usually pretty huge. So when you get this kind of thing, often many of the species, if you look up where the thermal came from, it's some lousy method, and so you do better to replace it, even if you're not completely consistent. Now some of them are not. So for example, CH3 there, probably there's some perfect number from thermochemical tables and it's completely nailed down to 5 decimal places. And so you'd be foolish to try to do anything with that. So you really have to look into it. But it is a worry. For example, we have right now, we have a lot of CBS QB3 numbers. We have a lot of really rough group activity estimates kind of from Benson or from Fazeli from a million years ago. And then now we're starting to add like F12, CCSD numbers and stuff. And I don't think anybody knows what exact systematic errors were introduced by doing that.
Do you actually go back and with that CH3, you compute it both with the CBS3 and then also pull up that number to 5 decimal places and maximize your cancellation errors instead of suggesting that you just take the very best you can get?
Currently right now, mostly what my group does is mostly just tries to get the very best numbers for each one separately, because we don't know how they're going to be used, and we don't have a big enough set to make everything consistent. But it's definitely a potentially problematic thing, and occasionally we run into cases where our best numbers are from different levels of theory, and you have to worry about what's cancellation. And then so some people, actually Deminda, for example, they work on like different isodesmic schemes and other ways to try to reduce the sensitivity to the method. But I would say this is definitely a work in progress about doing that.
Yeah, thanks for the question. All right, last note, we already noted that we can just conclude many of the reactions we're sensitive to do not include the observable we care about, and typically there are bottlenecks for the formation or consumption of the species we care about. Great. So that was case study 1, the first example. The second example should go quicker. We already know the basics. Ethylamine oxidation, same molecule, now with oxygen. It's very diluted, 500 ppm of ethylamine, that's it, and a factor of 4, so it's not stoichiometric, but it's close to stoichiometric. We can see here a semi-ignition or inflation in radical. For non-diluted system, you'll really see a large or sharp ignition. Here you just see an inflation in OH radicals. Just a mind exercise, if I were to choose a certain rate which the system is sensitive to and change the rate coefficient, what would I observe here? So here's just something I drew, not based on any calculation, just to emphasize the point that we can have just one rate that might be a bit faster than the reference state, and we can shift the simulation result. And now once we see that, we can try to visualize how will the sensitivity coefficient versus, sensitivity coefficient versus time will behave. What will we see in the graph before we see it, just for our understanding. At early times, nothing really happens. Then we see suddenly we have a positive change. Later on, it becomes smaller and a negative change. I think it's important just to understand what to expect. And here's a sensitivity analysis for oxidation. We could really see such a behavior, for example, for reaction number 1, the combustion reaction, H radical plus O2 giving O plus OH, so we generate OH radicals here. All right. So that's the sensitivity coefficient we see here for number 1. Yes, please.
So from the chat, while talking about sensitivity, I saw the presentation is on sensitivity analysis of concentration of thermodata. And sensitivity analysis has been done on laminar burning speed or ignition delay time. Does this help improve the mechanism also?
Excellent. So here there's an excellent question being brought up. Everything I've spoken about was sensitivities for kinetics or thermal. Definitely, you can run sensitivities for a system observable, not just one rate, for ignition delay, for flame speed. So that's an excellent first comment. Then the question was, will that help to improve the model? Depends what you want to do with the model. If you would like to model ignition delays, definitely. And so again, depends what the model is aimed to do. And generally, all sensitivities analysis tell us something. If we can have an action plan with it, if we have something to calculate or an experiment to perform, of course it will improve the model. But I come again to the point of what the model is trying to predict for you. So I won't go into all the details. I think by now everything should be more or less understood. Let me know if you have any questions. So that was a very brief example. Just want to show ignition and how it looks, just because it's common. And thanks for the comment that we can also have sensitivities for a global parameter such as ignition delay, and not just in species observable concentration. A third and much more complicated example is a pressure-dependent network. I'll go very briefly, and I won't go to all the details. First, Professor Green will discuss pressure-dependent networks just today afternoon. I won't go into all the details. What I will say, you see here a nice potential energy surface calculated at a nice DSP level for geometries and CCSD TF12 with a nice basis set for energy. Quite a nice potential energy surface for N3H5. So we care about, I'm always pressing the wrong button. So we care about N2H3 reacting with NH2, and they can do all sorts of crazy things. The dashed lines are direct bimolecular reactions, so normal reactions as you would have thought about so far. The solid lines are pressure-dependent reactions. They're unimolecular. either you're forming a unimolecular product or that product unimolecularly decomposes. So again, Bill will explain pressure dependence and a theory behind it later today afternoon. All you need to know just for now is that these two species can collide. They have a certain energy. Here is 0, but you say 0 is quite high. They have a certain energy. Once they collide, they keep that energy, right? Energy conservation, until they can lose it with a collision. So a bath gas, let's say nitrogen, argon, whatever, or other species in the system might collide with them. There's energy transfer, and then if they're excited, if they're hot, then they'll lose energy, and slowly or fast, depends on the pressure, they'll give you a product. The point is, they're formed excited. If they're not being cooled down or lose energy fast enough, they stay excited in that system and they can move around on all these solid lines. They can also form one of the products, whatever, if they have enough energy, without forming the middle one, skipping it. If that wasn't perfectly understood, that's okay. You will hear all about it today afternoon. So everything you need to know practically for now, these species can directly form, let's say, these products in a pressure-dependent mechanism, and not just by abstraction or anything, or disprop or anything else. So technical details will follow. And what I wanted to show here is a very different case and very complex of sensitivity analysis for a pressure-dependent network. These sensitivities were produced by ARC. ARC is a software we haven't discussed in this workshop. We might discuss it next year with other software as well. And ARC tells us at each pressure, 1 bar or 100 bar, what are the sensitivities of and observable to the energies of the wells. And now we're thinking about things differently. And observable here isn't a species concentration, and observable is a reaction rate. Very confusing. Before, we changed the rate to see the change in concentration. Here, the pressure-dependent network helps us calculate a rate to feed into a model. So that's our, you can call it an observable, the product, the rate that we care about. And the rate is sensitive to the energies of these wells or transition states, as you can see here. And it's sensitive to them differently at different pressures. And the analysis is pretty complicated, and we haven't covered pressure dependence, so I won't go into all the details now. I do want to go over with you on the last one, which I think we can do together. If you'd like all the details, the study will be published this year soon. So let's look at the last reaction. The last reaction is N2H3 plus NH2. So that will react, forming the singlet H2NN plus ammonia. So here it is, that will. So a direct pressure-dependent reaction from here directly here. And here are the sensitivities. Let's just see what it means. It means that if you were to change E0, you can think about it as the enthalpy of that well. If you perturb it, if you increase it, you'll get a higher rate. You'll get a different effect at different pressures, but a higher rate. And if you change the transition state, you get a lower rate. It all makes sense. We just said that everything you need to know for the analysis is that these species collide, they form an excited complex. If the pressure is high enough, you're going to lose it, and it forms that very stable well. At low pressures, it might roam around past that transition state, which is submerged, so it has higher energy. You can pass it and form that. I'll get a higher overall rate if the gap here is larger. That's all. So how do I cause the gap to be larger, or how do we get that effect? If the first reactant well has higher energy, right, I will get a larger gap here. And I have more chance of the excited complex to react by that channel. If PS3 is lower, I have a larger gap as well. And that's what we see here. If you change the energy of the entry channel, that's how we call it, the first well, if you perturb it and increase it, you get a higher rate because you have a higher gap. If you perturb TS3 and increase its energy, we always increase in the, you get a lower rate because you just increased it, you get a tinier, a smaller gap. There's a different effect at different pressures. At 1 bar, you can see here the blue horizontal bar, the sensitivity coefficient is slightly larger than at high pressures, 100 bar. That's because at high pressures, that excited complex is going to fall apart or not fall, it's going to lose energy and be stabilized as the well. So it's not going to pass through that channel anyway, so we have a much slower effect. That's principally all I wanted to show here. I know there's some material that wasn't covered in the workshop, and if you haven't seen these kinds of systems, it's harder to understand everything in just 3 minutes. But just so everyone aware of that kind of sensitivity analysis as well. Questions? Questions? Great. So I was happy to show the last example. Okay. So how do we calculate sensitivity analysis? We have several ways to do that. You can first, I'll start with that, generate a model with RNG. RNG will spit out your sensitivities if you ask it to do so. We'll do it right away. I'll show an example. You can also take the model from RNG and run it into RMS. And Matt was kind enough to show us yesterday how to get sensitivity analysis from a model in RMS. You can also use Cancera. You can also use Camping. If we'll have time, we can also show one of these. And you can use Arcane, a software we have not discussed in this workshop, to get pressure-dependent networks. It's a daughter of RNG. It sits within the RNG repository. In other words, if you install the RNG, you have Arcane as well. And you can look up the RNG website to see exactly what it does and how to operate it. You can contact us, and hopefully you'll hear more about it next workshop, next year. So before I show an example, let's conclude what we have so far, what we did today. First, running sensitivity analysis is crucial for improving a predictive model. Note that that predictive is involved. Oftentimes, people fit a model. I'm not judging. It might be a very good thing if you don't care about chemistry, you don't care about predicting at other conditions. All you care about is to simulate fluid dynamics at certain conditions. You need a chemical model. It could be true, it could be non-realistic, whatever. You need something that actually works. When I say true, I mean it could be based on true physical data, and it could simulate the physical reality based on fitted values, and that's okay. So people might fit a model. They do that using sensitivity analysis. They see which reactions govern the behavior of their observable, and they can tweak it around. You get a non-predictive model, a very fixed model for your conditions. That's okay. What we're doing here, I hope, is trying to build predictive models. We benchmark them to known conditions, and we use the sensitivity analysis to improve them, but we're not tweaking or fitting them. And so it is part of the cycle. And don't neglect thermal, as we showed in the example. It might be even more important sometimes than kinetics. Both are important. Sensitivity analysis assists us to understand the dynamics of the system, as we showed in the first example in depth. Directs us to parameters that need to be better determined, either experimentally or computationally. Should be combined with an uncertainty analysis. So parameters we're sensitive to, but we know them with a high accuracy, like CH3 radical. You saw that we're sensitive to it, but it's pretty well known. I'm not going to do anything with it, but parameters I'm sensitive to, and I have uncertainties, large uncertainties in their values. of course, I'll try to improve them. And that's what our process of developing a model is. It includes running sensitivity analysis. And sensitivity analysis is part of the routine of generating and improving a predictive kinetic model. So that's all for the presentation. We still have some time, and I would like to show you an example of how to run RMG and get sensitivity data out of it. Before I shut down the slides, any questions about anything we've done today? All right. So, let's see. I'm going to show an example of running RMG for a small model and getting sensitivities out of it. Max, can people see, or Matt, can people see
Yep.
my
Yeah.
screen? Yes?
Yep.
All right, great. I don't have a prepared example on purpose. I would like to do everything with you because it's a great exercise. Let's start. It's a bit awkward for me because I'm sharing my screen, so I don't see it on my screen, so I'll look at the board as well, at the screen, the large screen as well. So I might click the wrong button because I'm not seeing exactly, it's not that convenient. Great, let's start. Let's open an arbitrary folder, which I already opened, and I'll delete everything here. That was my example. I just verified that things work. Let's start from scratch. We want to run RMG, and we want to tell RMG that we want sensitivity analysis. And so I already have RMG on my computer. I assume you all do as well. If you have the developer version, you have examples as well. If you don't have the developer version, you have binaries. You can download examples from the website. Here are examples. Let's see RMG's example. What did I take last time? Let's take ethane oxidation. Whatever, here's an input file. I'm copying an example of an input file because I'm not going to write it from scratch. I've dealt with RMG for several years. I don't remember all the sections, and I'll definitely make some mistakes. So I'm starting off with something familiar. Here it is, input file. All right, here's an input file. Some data sources, libraries. I'm not going to deal with libraries. I don't care if the model is correct or not. You can tweak it later. We have ethane oxidation. I hope it won't take that long. We'll see. Termination time, let's make it much smaller so it will not take that long. Great. So this input file is a generic RMG input file. It doesn't tell RMG to run sensitivity analysis. So let's tell it. How do we tell it? What's the command? Anyone knows? I certainly don't. So I don't remember. How do we get to it? Let's open the documentation. RMG. Documentation. We want to see some RMG stuff, not arcane stuff, so we'll click RMG's user guide. Here are creating input files. Definitely within that we can find something related to sensitivity that can guide us how to run sensitivity analysis in RMG. Control F, sense. All right, sensitivity. We have many things we can do. We can define in the reactor block what species we want RMG to calculate sensitivity coefficients for, what are our observables. And we can give a sensitivity threshold, which means in the sensitivity analysis, don't include all the reactions in the model, just use a threshold to filter them out. I'm not that certain exactly what the procedure behind it, how it filters them, but we'll go with it. And there are other parameters as well. We don't need them right now. They're not essential. For example, if you use ranged reactors, something, a nice feature in RMG, you can specify other parameters as well. You can specify the tolerances of the sensitivity, absolute and relative. If you don't, you'll get the default values, and these are the default values. We'll just go with it for this example. So I'll just copy that part. That's the syntax, and we'll modify it accordingly. Here is my input file. I need to go to the reactor block and just add it here. CH4H2 are not species I defined. I defined ethane. So let's calculate sensitivity analysis for ethane. If you want sensitivity analysis for an intermediate, which isn't specified in the input file, you should first, well, you know your observable, so you should specify it in the input file in a species block. Don't specify an initial concentration or specify 0, it's equivalent, and you can use it here. So you just need to define the species, define the name label that you're going to use. So I'm using ethane. Ethane is perfectly defined here. RNG knows what it is. It has a structure and everything. Great, that's all you need. Done. So what did I do? I took an example, I modified it, and added from the documentation. I don't know by heart. I added from the documentation the directions to run. I'm saving that input file. Here are the directions to run the sensitivity analysis. Let's run it. We can close the documentation. So here's my input file that I just saved. I'll open up a terminal. I'll activate my RNG environment. Great, let's run it. $sign RNG is the path to my RMG repository /RMG_py, which is the executable that I want to run, and I'm sending my input to that executable. Let's do it. So RMG loads up all the database. I hope that's the longest part and that actually running it for our example will be fast. So currently RNG is training its database. It has training reactions, as you learned. It spits out some warnings here because I haven't defined any thermal libraries. So for training the data, for reactions that might not be relevant for my model, it had to come up with some assumptions of thermal data, and it didn't have any libraries I defined, so it got some not that good values. It is aware of that, and it warns the user. Well, that's okay. I know I didn't define good libraries. Great. Running the model, enlarging the core, running some pressure-dependent networks. I didn't mean to do that. We can rerun it maybe without the networks. All right. That wasn't planned. No problem. We'll let it run. It might terminate soon, but let's remove pressure dependence in a new folder and run it without. No P-Dep. I'll just run it here. So here's another input file. It terminated. Great. That's nice. 1 minute and 40 seconds, including loading the database. And it did run pressure dependence, which usually takes a while. So conducting sensitivity analysis, it's a post-processing script. Tomorrow we'll learn about script, and we'll see that you don't have to, let's say if you have a very long model that runs for hours or weeks, and you forget to run sensitivity analysis for an RNG, you don't have to rerun the model. You can just run sensitivities, and we'll see that tomorrow. Today we did it inside the input file, and great, everything's done. So we don't need to run no P-Dep. Let's see the output. The output, the sensitivity output, will be in Solver, the Solver folder. Here it is. We have a CSV file, comma separated values, that you can export to Excel and plot whatever you would like versus time, whatever. And here we have sensitivities of rates, you can see the reaction. Your observable ethane was most sensitive to. Here's a horizontal bar plot. If you want to plot it versus time, use the CSV file and do that. And it also automatically spits out the sensitivities for thermal. And I actually forgot, and maybe one of the other developers can help me out, at what time does it output that?
So it's the maximum over the entire time interval. So it will calculate it as a sensitivity at every point, and then it just takes the largest, or the largest in magnitude.
That value and that value could be at different times?
Yes.
All right, so I'll repeat that. It's not at a particular time. It's the sensitivity of ethane to, let's say, delta G of H radical, the highest sensitivity observed at the entire time span of the simulation. And that could be a different time. You might, so it's nice if you're developing and you quickly want to see what you're sensitive to, and you're developing a model, great. When you present the results, I'm not certain that's a common way to present, but it is great to develop a model. And wonderful. So I think we're just on time. We can take soon a break. And that was everything I wanted to show you. Guys, use sensitivity analysis. It's great. I love sensitivity analysis.